of a sphere.
Yep.
Yeah, sure. You can start here.
Alenka?
Hi, everyone. We learned in high school that the formula of the surface area of a sphere with radius r is V equals 4 on 3 by r to the power of 3, whereas the surface area S is 4 pi r squared. Clearly, S is the first derivative of V with respect to r. Our focus is to investigate the derivative of this formula and explain why one is the derivative of the other. And does this relationship hold in higher dimension? Let's get started. Our group will be looking at the surface area and the volume of a sphere. This relationship can best be described by looking at the relationship between the area and circumference of a circle. Let's start by understanding integration. Integration is a way of summing up small items to find the whole. We'll be looking at a big circle as a series of an infinitesimal smaller circles. So by integration, we'll add up the circumference of these infinitesimal circles with r radius. Next, please. But before that, we need to understand these small circles and its circumference formula. The ratio of the circumference to diameter of any given circle is approximately 3.14, which is called pi. If we are to make the circumference as a subject of the formula, then we will have pi times diameter. Don't forget that diameter is 2 radii. Hence, we have pi times 2r, which is 2 pi r. We will now add up these infinitesimal small circles with 2 pi r circumference. Note that as the small sizes approach 0 in width, as the circle approaches 0 in width, our answer approaches the true value. So our boundaries would be from 0 to big R. Here we are integrating 2 pi r from 0 to big R with respect to R. We can take the 2 pi outside as it's a constant. So we are left with R. The integration of R is R squared on 2. When executed with our boundaries, we have 2 pi big R squared on 2, which is the same thing as pi r squared, the area of our big circle.
Christopher?
Similar to finding the area of a circle, finding the surface area of a sphere, we also use the onion method. In this instance, we need to think of a sphere as many circles stacked on top of each other. To find the surface area, we must sum the circumference of all of these infinitely small circles. Although these formula may look complicated on the screen, in layman's terms, it is as simple as taking the formula for circumference of a circle and the diameter of the very small circles and adding them together and integrating them. That is a very simplified explanation. There are a few more steps involved, obviously, but basically we can find the surface area of a sphere by performing an integration on infinitely small circle circumferences. Yet again, to find the volume of a sphere, we can use the onion method. We can determine the volume of a sphere by finding the sum of many infinitely small spheres' surface areas stacked together to form a larger sphere, like shells of an onion. This is obviously very similar to the method used to find the surface area of a sphere. Essentially, a sphere is made up of a huge amount of sphere-shaped shells, each with an individual surface area. The sum of all of these surface areas is equal to the volume of said sphere.
All right. And we want to know the general relationship for this, the relationship between the volume and the surface area. We followed Dr. Payam's video on in showing how you can draw this relationship or show that this relationship holds in greater dimensions using the divergence theorem. The three-phase step would be to first, in the first two phases, to show a volume equation, a general volume equation for a unit ball, in terms of just with the integral of an nth constant bounded by a ball in r to the n dimensions, which is phase one. Phase two, we introduced the divergence theorem, which shows that the surface integral of the vector field of a closed surface would equal to the volume integral of the divergence over the region inside the surface. And eventually we would get the volume equation in terms of surface area. And then in phase three, we would try to equal both volume equations and attempt to show a function in terms of surface area. So this is our document, and phase one goes to the middle parts of the document, and phase two goes to the end. In phase three, you can see after phase one's formula is v equals to cr to the power of n. Phase two, we eventually figured that without going too much deep into the formulas, v equals to r over n times the surface area. When we related both equations, we eventually get the surface area equals to c times by n times by r to the n minus 1, which clearly shows that it's a clear derivative of our first phase's equation, v equals to c to the power of, c times r to the n. And we just wanted to explore like the relationships between the volume of a sphere and the surface area of a sphere in greater dimensions. And as we can see, at the fifth dimension for volumes, so to speak, the constants of the constant in the last slides, they start to shrink at the fifth dimension for volume, as well as they start shrinking for surface area at the seventh dimension. And this is just a basic relationship and what the nth sphere would look like essentially in greater dimensions. And yeah, do we have any questions?
Done?
Yeah, that's done.
Okay, so we go to your colleagues first. It means in the group, not in this group, in the class. If they have any question, please.
No, I just wanted to say well done. Thank you.
Thank you.
Okay.